Okay, so as I was saying, we look at a couple of different diode models that we use to make perform quick and easy analysis of diode circuits. Now, straightforward analysis is not always possible, nor is it always easy. Okay, but with approximate models of semiconductor devices, we can often make a pretty good case for the actual device parameters. So let's take a look at the first one. So in these models, we're going to model the diode as either being on or off. Okay, so there's two of them. One is the ideal diode model. The other one is the constant voltage drop model. Okay, and let's see here. Okay, and the only difference between the two is that in a constant voltage drop model, we require a certain amount of voltage to turn the diode on. So again, a diode is a two-terminal device, and it is also a one-way device, right? Current flows from anode to cathode. Anode is positive, cathode is negative. Okay. So this is ID, and this is VD. Now, because this is a nonlinear device, voltage and current have a nonlinear relationship, so we can use approximate models. And so the models that we're going to use are ideal diode and constant voltage drop. Both models, in both models, we are going to say the diode has only two states. So like a switch that we saw in the last previous lecture, it's either on or off. Okay. When it's on, it behaves like a short circuit. When it's off, it behaves like an open circuit. All right. So in that case, or in this case, the model assumes that the diode is behaving exactly like an electrical switch. So again, if it's on, it behaves like a short. If it's off, it behaves like an open. Okay. You all with me so far? Okay. All right. So now what happens when a switch is turned on? If the switch is turned on, it allows pathway for current to flow through. Same thing for a diode. If the diode is on, current is flowing through the device. So diode current ID must be greater than 0. Okay, diode current ID must be greater than 0. So you have two terminals. And if there's a short between those two terminals, current is flowing, so it must have a positive value. What about diode voltage? If it behaves like a short, what can we say about the voltage across those 2 points? Fundamental concept. You have two nodes in a circuit. If both nodes are connected together by a wire, they are the exact same electrical potential. It's the exact same electrical potential. That means there is no difference in electrical potential between those 2 points. Voltage is potential difference. If the difference is 0, voltage is 0. If you measure the voltage across the two same nodes that are connected by a wire, voltage will always be 0. So if the diode is on, voltage must be 0. Current must be greater than 0, must have a positive value. Voltage would be equal to 0. Does that make sense? Right. On the other hand, if the diode is off and it's replaced with an open, then current ID is equal to 0 because current needs a pathway to flow through. If your switch is open, there is no connection, no pathway available. So there is no current flowing through the circuit. Hence, ID must equal 0. Okay, ID must equal 0. And then VD would be less than 0 volts, because this state of the diode would be the reverse bias state, meaning you're trying to force the diode to work in the opposite direction, which it wouldn't work because it's a one-way device. So the voltage would be negative. The negative in the sense that VD, as measured with a positive reference at the anode and negative at the cathode, that means the cathode is higher than the anode. Okay. So the diode cathode voltage could be 5 volts and the anode could get 3 volts. Well, because the cathode is higher than the anode, diode voltage VD would be minus 2 volts, less than 0. And in that case, diode is off. Okay, diode is off. All right, let's take a pause and then let me know if you have any questions, and then we'll talk about these graphs and charts. So the question being asked is, if I understand correctly, does it have any resistance? No, the diode will not have any resistance in that case. Hence the term ideal diode and constant voltage drop. So it's a very good question, since we said that real life diodes have a model of a diode series resistor, which is RS. In this case, RS would be equal to 0. Absolutely no resistance in the pathway. Okay. All right. So based on these two states and these statements, let's look at these graphs. Look at the ideal diode first. What do we see? In an ideal diode, the characteristics are shown in red. The one in blue is a real life diode. Okay. Real or practical diode. And this is the model. Okay. And what it says is, if the voltage that is applied to the diode is less than 0 volts, meaning negative, then the diode voltage is negative and the current stays at 0. Okay. And when it turns on, diode voltage is at 0 volts, whereas current increases because it's allowed a pathway to flow through. Hence the characteristic is simply a corner turn like that. Okay. And that is based at 0 volts. Okay. Does that make sense? Okay. The constant voltage drop is exactly the same as the ideal diode model. However, the CVD model takes the approximation a bit closer to a real life diode, because real life diodes require a certain amount of voltage to turn on. So the CVD model in reverse bias is exactly the same as the ideal diode model, meaning in reverse bias, CVD model is the same as an ideal diode, meaning it is off. So I would say two states, on and off. And in off, it is exactly the same. So it behaves like an open circuit. ID in this case would be 0 and VD would be less than 0.6 or 0.7 volts. And I will explain what this means. Okay. But as far as the current goes, current is equal to 0. Okay. Now, ideal diode does not require any voltage to turn on. You could say even at 0 volts, if both in the same, it would automatically turn on, provides a short circuit, so the voltage is equal to 0. In CVD model, it mimics the voltage that is required to turn on, meaning if it says the turn on voltage is 0.6 volts, then the diode is modeled as a voltage source of 0.6 volts. So when it's on, it behaves like a short plus voltage source and the voltage source is supplying a voltage that is equal to the voltage required to the turn on the diode. So the turn on voltage of the diode. This turn on voltage can be 0.6 or 0.7, depending on the book or depending on the author. Some books would use 0.6, some books use 0.7. In a problem statement, it will be provided. If it's not provided, you can always assume. The thing with these kind of models and these kind of circuits is we can always make a lot of assumptions. So if there are quantities that are given if there are quantities that are not given in the problem statement, you can always make an assumption. Okay. This would be either 0.6 volts or 0.7 volts. What this means is if we are using a CVD model to describe our diode, to analyze a circuit, and the voltage across the diode is only 0.5, then a diode does not have sufficient voltage to turn on. So it will remain in the off state. Whereas in the ideal diode model, if you apply 0.5 volts, diode is going to turn on. Right? Does that make sense to everyone? Right? CVD model is exactly the same as an ideal diode model. The only difference is ideal diode does not require any voltage to turn on. CVD model requires the diode turn on voltage. And after the diode turn on voltage, behaves exactly the same. It's a straight line going up. And the voltage is held constant at that point, and the current increases rapidly. Because it's now a short circuit, it allows current to flow through itself. Okay, and that's the big difference with a CVD model and the ideal diode model. In this case, V on, the turn on voltage, is about 0.7 volts. Okay, any questions? No good? Okay. The way we usually do an analysis, let's say we have a diode circuit and we want to find either the diode voltage or the diode current, right? So we make an assumption about the diode state based on the circuit conditions and based on the knowledge that we have, right? So if we take a look at this circuit right here, we simply have a voltage V in source through a resistor. It's connected to the diode. And we want to find out what the voltage transfer characteristic would be. Meaning if we apply an input voltage, what would be the output? Okay. So let's say this was not a constant voltage drop model. This was ideal diode. If it was ideal diode model, how would we analyze the circuit? Well, what we need to do first is we first make an assumption. So assume a diode state. Do you think the diode is on or do you think the diode is off? Right? So assume diode state on or off. Then replace the diode with its equivalent based on your assumption. If you assume that the diode is on, then you replace it with the short circuit wire. If you assume that the diode is off, then you simply remove the diode from the circuit. So it's an open circuit. So you replace the diode with its equivalent based on your assumption. And then you analyze and determine the voltage and current. Okay. Analyze and determine the voltage and current through the diode. And the results, well, you check your results against your assumption. Okay. So if you assume that the diode is on in the first step, perform your analysis, and then you determine your diode voltage. At the end, you verify. If it was on, your diode voltage must be 0, and your diode current must have a positive value. If it turns out that neither one of those is true, then your assumption is incorrect. You go back to the beginning, you make a different assumption, then you redo your circuit, or sorry, you redo your analysis. Okay, there's only two possible states, so there's only two possible analyses, right? In this circuit, it's rather straightforward. If I'm applying a voltage, and if it's positive, the diode is on. If it's negative, the diode is off, right? And so if it's on, I replace it with a short circuit, perform the analysis, determine the current, and then verify it against my assumption. Okay, we are out of time, so I'm going to end class here today. We'll pick up here again on Wednesday.